Hi, everybody, and welcome to another session of Math 103. I hope this again finds your family doing well and you feeling well and us getting through this crazy period of time. But what are you going to do? You know, we gotta move along. So here we go for our next session on Mathematics 103, as I mentioned earlier. Okay, today we're going to take a look at some stuff that you haven't thought about probably for a little while. Okay. I want you to take a look, if you would please, at this crazy looking figure. Well, I don't know if you remember what this is, but I did mention to you earlier, in maybe the last video or two, something about the word polygons. Now, I want you to kind of brainstorm in your head what you think a polygon is. Now, if you look at this particular figure, you can see it's made up of sides here. There's, I guess, 5 sides on this thing. And the sides, what are they made out of? Well, if you think of it in geometric terms, they're line segments, right? So for brainstorming what a polygon is, it's something that has sides that have line segments, that are made of line segments, all right? Is it kind of all over the place as far as being in 3 dimensions, or is it flat? Well, you can see it's lying on a flat screen, right? So a polygon has to be flat. It has to be a plane figure or lie flat. So that's another important part of what a polygon is. So it has to be a flat surface figure. It has to have sides that are line segments. Okay, can it be a religious figure? What do I mean by a religious figure? That's another Kellyism, but can it be like in church and cross itself? What do I mean by that? Well, a figure that crosses itself would be one where you have a figure which has line segments that would look something like this, go like this, then it would go like this, it would go like that, maybe like this, down like this, and then back over here. That figure is definitely crossing itself. So a figure that kind of crosses over itself like that on a plane is usually referred to as a complex figure. And of course, the opposite of being complex is simple, right? So, okay, so it appears this is no good, right? So let's get rid of that, okay? Let's take that. Well, I can't get rid of it that way. I guess I'll have to get rid of it this way. I'll just have to pick all of the pieces and make them go away. See if I can get them to, now they're not doing what I want. There they are, maybe now. And let me get this one. Oh, now I lost that one. And we'll delete them all. Okay, whoop, we missed one. So let's get rid of that one. Okay, so it's got to be simple. It has to be sides that are line segments, and it has to be flat. Well, can this be a polygon? There's a Well, no, that can't be a polygon either, because it isn't what? It's open, right? It isn't closed up. So it has to be a figure which is closed. So that's no good either. So I think we've got all the pieces maybe we need to describe what a polygon is then. It has to be simple, cannot be complex. It has to be closed. It has to close itself up. And it has to be a plane figure which has sides that are what? Line segments, right? So let's take a formal look at the definition of a polygon then, right here. It is a simple closed plane figure that with sides that are line segments, okay? So there is the best definition I can think of for a polygon. So if you want to write that down, you may do that. If you're taking notes, you might want to write that down because we're going to talk a lot about polygons over the next few days. Okay, now, this is another typical polygon, okay, very similar to the one you saw before. Okay, in fact, it might even be the same one. What do you suppose we could do to determine the measure totally of all the angles that are on the inside of this figure? Well, I think all of you are quite aware of the fact that in a triangle, the three angles on the inside or on its interior have to add up to 180 degrees. So what might be helpful here is if we took this figure and we split it up into triangles from one vertex. So let's try that. Well, let's see. Let's use this vertex right here. And let's hook that up there. So there's one triangle going from the same vertex. Let's draw over here. So there's two triangles. There are actually three triangles in this figure. So how many degrees would the angles of this figure have to add up to if we can split it into three triangles? Well, it would simply be what? It would simply be the answer to 3 times 180 degrees, or a total of 540 degrees. Now, you might be asking yourself, why is that important? Well, it's important to something I want to show you later, all right? And I'm not going to expect you to know that formula, but it's something that will help us describe some stuff that's coming up ahead of us, okay? So keep that in mind. Okay, what do you think a regular polygon is? Well, to go back over here, does this polygon look regular to you? No, it's kind of weird shaped, right? Kind of a weird shape. So no, it doesn't look too good, all right? So when we think of a regular polygon, we think of something like maybe a square or maybe a stop sign or something like that, okay? So let's take a look at what the definition is for a regular polygon. In order for a figure to be a regular polygon, okay, whoop, I've left the drawing tool on, so let me shut that off. Left that on, sorry about that. A polygon which has all of its sides all the same length or congruent, and, okay, let me get this thing out of here, and all the interior angles are identical in measure also, okay? So a regular polygon then is a polygon you're more used to. It's a polygon in which all the sides are exactly the same length, or, you know, the geometric word for that is congruent, and all the interior angles are identical in measure. So if you've had a chance, it might be a good idea if you jot that down. All right, now, how about the interior angles of a regular polygon? How could I get how many degrees are in each angle on the inside of a regular polygon? Well, we already know how to get the number of degrees that exist in any polygon. You just take 180 degrees times what? Times the number of triangles you have. Well, the number of triangles you have, if we go back to that particular question, back here, we look at the number of triangles, you'll notice there were 3 of them, right? And of course, how many sides were on this figure? Well, there were 5, right? So it appears that the number of triangles might be 2 less than the number of sides, right? So the actual formula we use usually to determine the number of degrees in the total number of degrees of all the angles inside of any polygon is really, looks like this. It is 180 degrees times n minus 2, where n is the number of sides on the figure. Now, with that in mind, if we go back here and take a look at the formula we could use to determine the measurement of every single angle, because they're all going to be the same in a regular polygon, okay? I wonder what that formula would look like. Well, it would have that 180 times n minus 2 in it, but what would you have to do with it? Wouldn't you have to divide it by the number of sides you have? Because the number of sides you have on a polygon is exactly the same as the number of angles that are in the polygon, right? So that's where this formula comes from that I'm about to show you right here. The formula is the measure of the interior angle of any regular polygon is equal to 180 degrees times n minus 2, where n is the number of sides. That's the number of triangles, in other words, times 180. And then that gives you the number of angles within the polygon, and you divide it by n, which is the number of angles, same as the number of sides, and that'll tell you the answer to the question. So for a regular pentagon, for example, then, it'd be 3 times 180, or 540, and then you would divide 540 by 5 to determine the number of degrees in each interior angle. And I believe that would be 108 degrees, or each interior angle in a regular pentagon, okay? All right, let's take a look at some of our regular figures here, okay? You can see the first figure up to your left is an equilateral triangle. It has 3 sides, and you know that some of the angles are 180 in there, and therefore you know each angle is 60 degrees. Is it important that you know that right now? No, probably not. But you should be able to recognize that this is definitely a regular polygon. Okay, here we have a square, and of course you know squares all have 90-degree angles at their corners. So 4 times 90 is obviously 360. We already went over the pentagon, which is regular here. Those are 108 degrees. For the hexagon, which is the next figure here, 6-sided, okay? So you would multiply 180 times n minus 2, which would be 180 times 4, which would be, I believe, 720, and you would divide 720 by 6, which would mean each of the interior angles here are equal to 120 degrees. And of course, you're familiar with this guy right here, right? This is your typical stop sign, right? It is an 8-sided polygon, okay? And it's called an octagon. Now, will you have to know all these different gons? No, probably not. But you should be aware of some of the more common ones that you face in your life all the time. All right. Well, it's nice to be regular. What makes a polygon a regular polygon? It says sketch 6 different regular polygons and 3 non-regular ones. Well, I sketched more than that, okay? If you look at the ones on the top, there's your equilateral triangle I'm pointing to there, your regular pentagon. That looks like a 7-sided figure, so that's a heptagon, I believe. This is the octagon, and I believe this one has 9 sides, so that's a nonagon, and of course, this is a square. And then the non-regular partners that would go with those would be down here below. This is just a typical quadrilateral. This is a typical nonagon, but it doesn't have equal sides or equal angles inside. Same here with the octagon. Same here with the hexagon, or excuse me, the septagon and the pentagon, and also the scalene triangle. Okay, now that we've taken a quick look at a figure which lies on a flat surface known as the polygons, I would like to take a closer look now at figures that don't lie on flat surfaces, okay? All right, and what I'd like you to do is I'd like you to look at this picture that I'm going to make larger here of myself, and I'd like you to look in here at this particular figure right here. Now, it's hard for you to see what these figures are because we're dealing on a flat surface, a television screen or a computer screen. But you can see this is a box. It's a box that something came in, actually, that I got the other day. And these are what we call polyhedrons because they can't lie on a flat surface. If my hand represents the flat surface, it can't lie on that flat surface totally because it sticks out of it, right? So if you have a polyhedron, such as this one, okay, it has sometimes what we call faces and bases and all kinds of different stuff that we're going to be talking about. But a polyhedron is basically a figure which exists in space, all right, a 3D figure, but it doesn't have any curved faces. They're all flat faces, so they're all polygons, okay? So if we take a look at the definition of a polyhedron, let me make myself a little smaller here and get out of the way. So if you take a look at the definition of a polyhedron, it is a 3D space figure with, quote, sides that are polygons. Now, why did I put sides in quotation marks? Well, you'll find out very soon, okay? Now, if we go down here to the next term, what is a regular polyhedron? Well, this box that we saw earlier is certainly not a regular polyhedron because if you look at the sides, quote, here that I'm pointing to, they don't look like regular polygons, do they? And you can get the idea that a regular polyhedron has a situation where, okay, all the faces or all of its sides are all congruent, identical polygons, okay? Now, why do I keep saying sides in quotation marks? Well, let me talk about that. Let me make myself a little larger here so you can see this figure a little better, okay? Let's take a look at this figure again, all right? Notice what I'm pointing to right now is what we commonly refer to not as a side. It would be a side on this rectangle, but this side is not called a side. It's called an edge when you deal with a polyhedron, okay? Now, when you are dealing with sides on a polyhedron, there is no such thing. We don't call them sides. So these are edges here, and these things are called faces, all right? Now, you're going to watch a video by one of the authors of the textbook, and unfortunately, he's very careless with calling out edges and faces, and he sometimes calls them sides, and it can be a little bit confusing. So try to remember, this is an edge, like this one here. That's an edge. Up here is an edge, okay? But these are faces of a polyhedron, okay? So let's keep that in mind. All right. So let me reduce myself once again here. And let's go on. Okay, so let's go on here. What's up next? Well, what are these things? Well, notice these are three-dimensional objects drawn on a two-dimensional surface. And of course, you've seen these all your life, and you are quite aware of the fact that you have space figures or polyhedrons that look like this, but you can tell these are not regular polyhedrons because their faces definitely are not regular, okay? So when we draw a three-dimensional surface on a two-dimensional surface like we have on this screen, we have to show dotted lines to show where there would be faces which you could not see because the figure would block them. However, you know they're there, all right? And these are called something you're quite familiar with, I think. These are called prisms. In a prism, you have a base on the top and on the bottom of the figure that are generally parallel to each other. They don't have to be, but in most prisms you've dealt with in your life, the top and bottom base, if you will, are a shape that is identical. They are not necessarily regular, but they are identical to each other. Then all the faces are generally on a prism like this. This is called a prism, not a prison where some of you might spend some of your time of your life. Hopefully none of you will. But in a prism, okay, you have faces and you have bases, and the bases are identical, the top and bottom, and the faces usually are rectangles. Now these are called right prisms because they stand up with right angles at these corners down here in this area here, all right? This is another right prism over here. It's called a pentagonal prism because its base is a pentagon. This is called a hexagonal prism because its base is a hexagon. And of course you see here the typical pyramid shape. This of course is a pyramid which happens to be a square pyramid because its base is a square. And of course pyramids come to a single point at the top, all right? And the faces are usually some type of triangle. Well, they are triangles, okay? So there's some examples of prisms and a pyramid, which are, I'm sure, figures that you've dealt with prior in your life in the various math classes you've gone to before. All right, this of course is a triangular prism, okay? Its top and bottom are triangles, and of course its faces would be what? Rectangles, correct? Okay. All right, now, next, we're going to look at a particular type of polyhedron, the regular polyhedron, but there are some special cases of regular polyhedrons that are going to be of interest to you. So the next video you're going to watch from Professor Mike has to do with what are called the Platonic solids. So I'm going to close at this time. Oh, by the way, you're also going to see something about a soccer ball and what a soccer ball is derived from. It's a type of Platonic solid, as you're going to see, but it's not actually a Platonic solid. But I'll let Dr. Mike explain that. So with no further waste of time, we are now about to take a look at an introduction to the Platonic solids.